will switch gears again and talk about LC high resolution mass spectrometry, and I would like to show you that the use of stable isotopes could be efficiently used to tackle some very basic problems which we are facing in untargeted metabolomics. This has been said a few times already during the conference. The beauty of untargeted approaches are that you can really probe or try to probe the entire metabolic space, and you're open to detect the unknown. So you can measure the known and the unknown by these untargeted approaches, and they are definitely also the most challenging approaches in the field of metabolomics. Looking at a typical LC high resolution MS chromatogram, you have these three dimensions. You have the retention time, mass over charge ratio, and the intensity, and this has also been addressed a few times already. Usually you record about one or more mass spectrum per second. This results in spectra which are very rich and complex, about 1000 mass signals per spectrum, and if you do this on a chromatographic run like this, then you end up with millions of signals in a single run. And what you try to extract are these so-called features in every chromatogram. And to briefly define this again, what you observe, or what you try to get, is you try to extract a two-dimensional bound signal. So this has a dimension in retention time, and it has a dimension in mass over charge. And you define a certain width here and the retention time range, and you try to detect something which has a chromatographic peak shape in that mass window. And if you do so and try to extract all the features in such a chromatogram, and if you just imagine to look from top of such a chromatogram like this, and we apply this to a wheat sample, then the picture looks like that. So in this case, we used I think the most frequently used open source software, LC-HRMS, for extracting all the features present in that chromatogram, and we ended up with about 13,000 of these features. So it has also been said yesterday and today that this is more than biology can really tell us. So the question is, which one of those is carrying biological information? And this is due to this richness of the typical LC-HRMS chromatogram, the major challenges and basic challenges are associated to that. So looking at untargeted LC high-res MS-based metabolomics, major challenge is still the annotation of the sample related metabolome, and as directly associated to this is that it's very difficult even to validate an analytical workflow, because you have if you do not know if you're really measuring the biology or describe biology but something else, it's difficult to judge on the basis of these features if your extraction is working properly, or if the precision is okay, if matrix effects occur. You have to find something where you reduce the complexity of the data. Accurate quantification is also affected by matrix effect, has also been mentioned already. Identification of metabolites. All these factors are relevant. They're very basic, and I'd like to show you now that this stable isotope labeling can be used to address these things. In the afternoon there will be the workshop on the labeling techniques. I was asked to give a talk there as well, and I thought I will concentrate in the second part of my, or in the second talk, on this metabolic transformation and by the use of these stable isotope techniques. So challenge one, annotation of metabolome. What we use is an LTQ Orbitrap XL in our laboratory. That's what we use on a regular basis. We have access to other instruments as well, but that's the instrument we use most frequently. And to remind you of the principle, if you use highly enriched compounds in stable isotopes, in this case C13, and I'm going to focus on C13 and for the rest of the talk. If you measure the mass spectrum of this compound, you have a natural isotopic composition. In this one you have this mirror imaged, if it's highly enriched, at a mass interval which is at a mass which is higher than that of a non-labeled compound. That's obvious. And if you mix the two and do the mass spectrum, then you observe this mass difference between those. Immediately tells you about the number of carbon atoms in that molecule. And at the same time, which is also very important, if you think of feature extraction, if you use the C13 labeled material, all the metabolites are co-eluting perfectly. So there's no shift in retention time. You can really query the mass spectra to find this pattern. And how could you use this in untargeted metabolomics? It could be used. So you see, for different purposes, you always end up with this type of pattern. You can use it for annotation of the metabolome. You can use it for internal standardization and try to improve the quantification step. You can use it for tracer metabolization. You can use it for MS fragment annotation. And all of these things, we are basically working on that to use the isotopes to help us for these purposes. So I'm going to concentrate now on the annotation of the metabolome and the internal standardization. So the approach we have chosen has been implemented in a software algorithm which was written by a very talented bioinformatician in my group, Christoph. So we developed it together, but he's the one who knows how to program and handle the computer, which is very important in this field. So what is the purpose is, you have this complex spectrum, you try to find this pattern. So what the software does is you start from so every mass spectrum is inspected, and you start from any mass signal which is above a certain threshold, and then you say this could be a monoisotopic C12, and you just query every mass signal if it's corresponding to the distance which you expect for a labeled compound. And if one of these signals fulfills this condition, then it's looking for the isotopic pattern on this side and on this side. So this would be the one who are matching, and then the doublet, the monoisotopic and the fully labeled, are put on a positive list, and these are then binned to give a list of M over Z values, and these are then further processed and try to extract the chromatographic peak shape of those, and only those which can be observed for the C12 and the co-eluting C13 are kept. And this tells you then this is a feature coming from the biological composition, the biochemical composition of the sample. So this one example would be discarded. This one would be discarded because it's no counterpart on the non-labeled or labeled side. So then further the complexity is reduced to remove falsely detected isotopes. So the idea is in this whole procedure to only keep the M and the corresponding fully labeled, and in a final step, all these features which have been extracted are then grouped together to convolute the spectra, because many compounds show more than one single feature, and you want to describe the compounds in the end and not the features. So this can be used to define the feature groups, and if you apply this the software, then you can process a chromatogram like this, and you end up with these qualified MetExtract derived feature pairs, which are here illustrated. So the software extracts directly. It's capable of doing batch-wise data processing, and then you end up with a table with a data matrix containing the features. Each has a unique ID, and it's assigned to a feature group, which is then corresponding to the metabolite, and mass over charge, retention time, charge state, and then the number of carbons directly extracted and listed here. And then for each feature and each sample you have a pair, C12 and C13, which can then be used for internal standardization as well. So this gives you now the directly the number of metabolites present in the sample. It helps you with the molecular formula annotation because you have the number of carbon atoms, and it helps you for internal standardization because you have the C12 and C13 of all the metabolites present in a sample. So we try to show you the proof of principle, how this works with wheat organs, and we try to define how many metabolites can be detected by this method we have in use, and how complementary is the metabolic composition. Can this be differentiated? So what we did is we took a wheat plant, cultivated under regular conditions, and now meanwhile we have an own plant growth chamber where we do first experiments to cultivate the plants under C13 atmosphere to produce highly enriched material. And what we did is, so we cut the wheat ear, the stem, the leaves, and the roots, and these were analyzed separately. So, and we did 5 technical replicates from extraction to the measurement, and we also used 1 extract per of the fully labeled material, and pooled everything from this, and this pooled sample was used to internally standardize all these different fractions. So we could expect that all which is present in this mixture of this could be then matched in the plant sample, and then it was a regular procedure which was used in full scan measurement. And this shows you the chromatogram again with the 13,000 features, and if you apply the algorithm, then you see you end up with about 1100. So a tenth of that is only really carrying biological information if you consider the criteria we have set. And these features correspond to less metabolites, and this is about 500 in this sample. So all the green dots now tell you it's the most intense of these feature groups, so all the greens correspond to a metabolite. And this is also a nice picture because it tells you where the compounds really elute. And this is what we see very frequently, that we have something like a gap here in between. So obviously this is before the column is then flushed with a pure methanol in the column, and before there's a gap where nothing elutes anymore. But this is a very typical picture we observe. And if you look at a simple heat map illustration of these how these different organs behave, then you see at a glance that they are quite complementary regarding their metabolic composition. So this is of course not surprising, but this tells you now each of these lines with these 5 replicates tells you I'm a feature which really comes from the wheat sample. And this can be used of course for optimization of your extraction protocol. And what we did in this respect, first let me briefly show you. You can also then in this case the heat map contains all the metabolites which are shared between the different organs, but it shows the different concentration levels more or less in the different organs of certain metabolite groups. But you can also do and try to see how differentially is the metabolic composition of these wheat organs. So in total we found 600, and we said if at least 4 or 5 replicates should contain these metabolites, the feature groups. And then you see that the 160 metabolites are shared between all the different organs, and the root is a bit different from the others, carrying between 400 and 500 metabolites, and the root only has 270. And there's 160 metabolites which have not been detected in the root, but are present obviously in all the other organs. So this again is not surprising per se, but now every number really reflects a metabolite. And this is something which is ideally suited to be used for follow-up studies, for example. You can use all these on a positive list and do your regular experiment under C12 conditions, and then you can use this list of metabolites, which then can be in detail addressed for the biological question of interest. But this also helps you then for workflow evaluation or internal standardization. And to address this follow-up thing, where you could use with a small set of samples, because the C13 is quite expensive, to produce the positive list and do the biological experiment with many replicates, and then you establish from this minor experiment the positive list, and then can go into the interpretation of the biological experiment. So briefly addressing extraction efficiency and technical precision, how does it look like with this? So what I want to point out here is we concentrate on different extraction solvents and try to compare, and also use successive extraction, more than one extraction per sample. So what we do usually is to grind the sample in a ball mill, weigh in 100 milligrams, then this is extracted with a solvent composition 75 plus 25 of 25% of water. And then everything is spinned down, and the supernatant is taken and then spiked with the internal extract and diluted with water to bring it to a mobile phase composition which is compatible with the reversed phase chromatography. And looking at a comparison of 6 different solvents which we used, so ethanol with formic acid, then acetonitrile plus minus formic acid, and methanol plus minus formic acid. And what you see at a glance is again that this is highly suited to really address the question, how complementary are these solvents regarding the part of the metabolome which you can address with that. And you see that the formic acid obviously does make a bit of difference, but with and without formic acid, that's much more similar than between so the clustering is more so that for the same solvent the samples cluster together irrespective of if you have the formic acid added or not. Ethanol obviously behaved not so well in terms of extraction efficiency, but you also see that acetonitrile and methanol are largely complementary and can be used accordingly. So if we take as our standard extraction solvent which we have taken so far is methanol formic acid, and this looks quite good if you compare these, and we stay with this one again and look at successive extraction, then it tells you here again every line corresponds to a metabolic feature, in this case that the first extraction usually it's supposed to be, or it looks that it's quite highly efficient compared to the second and the third, and this one, the aggregate, is the quality control, should be black in the middle because it's a pooled sample of all these three. It again confirms that the whole system is very well behaving. Finally, very briefly, I'd like to address the technical precision thing. So if you do internal standardization, so this is the results again from ethanol water with 0.1% formic acid for the extraction, and then we have here 2 different wheat cultivars, and it was wheat kernels in this case, and here you see a histogram, so the distribution of the coefficients of variation regarding the precision. So we have 4 replicate extractions for each of these 775 features which have been found in all 4 replicates. So every feature gives you a coefficient of variation, a measure of precision, and if you look at the distribution of these coefficients of variation, then this 9.1 tells you this is the median value of the median of these coefficients of variation. So if you do this on the basis of the C12 features, you end up with about 10%, which is not too bad actually. So it's working, and if you look at the C13, you end up with about the same precision independent of the cultivar. And if you look at the internally standardized precision, then the median shifts to 3% and 2% for the two. So that tells you internal standardization, if you have on the basis of all these features which we have detected, is perfectly working here. And you can lower the technical imprecision to really low values which can give you a high confidence that the biological data you want to the biological samples you want to query really can be queried by that way. So this is basically what I wanted to tell you. I hope I could show you and convince you that this shows a very high potential for metabolomics research. This concept, and I'm convinced that it will become more common practice in the future. It's not available for, or it's not so common at the moment because it takes some efforts to produce the C13 samples and materials, but it's highly rewarding because it really improves what you can query and also in which way you can query it. And so the qualitative characterization of the metabolome does highly benefit, the quantification does highly benefit, and this topic will be addressed in the afternoon. So finally, let me thank the whole group, all the collaborators which contributed to this, and you for the laser pointer, and rest for the audience for paying attention and being patient with me. Thank you.